In Unit 7, we're going to be talking about the force of gravity and about the orbits of satellites and planets. Any two objects that have mass exert a force of gravity on each other. So a gravitational force exists between any two articles that have mass in the universe. No direct contact is required. The objects don't have to touch each other because the force of gravity is an action at a distance type of force. And the gravitational force always causes the two objects to pull closer together. That's why we call it an attractive force, because it causes the objects to attract each other. This picture shows Earth and a satellite above the Earth. And you can see that the force arrow on the left is the force of gravity that the spacecraft is exerting on the Earth. The spacecraft is trying to pull the Earth closer to the center of the spacecraft. The arrow on the right is the force of gravity that the Earth is exerting on the spacecraft. The Earth is always trying to pull the spacecraft toward the center of the Earth. The arrows are the same length because these forces are the same amount of gravitational force. But they are in opposite directions, right? Because Earth is pulling the spacecraft toward Earth, the spacecraft is pulling the Earth toward the spacecraft. They are Newton's third law pairs. R, in this case, is not the radius, although we typically use the symbol R to mean the distance between the centers of the two masses. And notice that the forces act on the line that connects the centers of the two masses. So the direction of the forces act on the line that connects the centers of the mass of the Earth and the mass of the satellite. The way that we calculate a gravitational force is given by this equation here. The gravitational force, F sub g, equals the universal gravitational constant, that's uppercase G, times the big mass. The big mass is represented by an uppercase M, times the smaller mass, which is represented by a lowercase m, divided by the square of r. And here r is the distance between the centers of the two objects. So the attractive force of gravity is proportional to the product of the two masses, right? Because it's a product because we multiply the big mass times the smaller mass. And gravity is inversely proportional to the square of the distance between them. Notice that G, it has a commonly accepted value of 6.67 times 10 to the negative 11th. And if you wanted to, because we'll be using this constant a lot, you could store this value in your calculator. That universal gravitational constant, given by the uppercase G, it's a very small number. It's times 10 to the negative 11th. And because this constant is so small, that means that one of the masses has to be very large, something like a planet or a moon or a star, in order for the gravitational force to be very significant. Just to give an example of that, we have here calculation of the gravitational force between the Earth and the Moon, and when we plug in the very large masses of these, of these planet and moon, we get a huge force, 2 times 10 to the 20th newtons. That's 200 billion newtons. But if we took another example of let's say a truck and a car, and the gravitational force between them, these are pretty large masses compared to us, right? We would have a hard time lifting them or pushing them around. But even though those masses are fairly large relative to us, when we calculate the force of gravity that they exert on each other, we only get 0.7 newtons. So it's a pretty negligible amount. So we now have two constants, both named g. Uppercase G is the universal gravitational constant. It's called universal because, as far as we know, it is the same everywhere in the universe. It does not ever change. It's always 6.67 times 10 to the negative 11th. Lowercase g, and we've been using that for most of this year, as the acceleration due to gravity close to the Earth's surface. But we treat that as a constant a lot of times. I mean, we typically say, oh, gee, that's 9.8. But really, the acceleration due to gravity will change depending on where you are in the universe. As you move further away from the surface of the Earth, g gets smaller. So the lowercase g on Mars would be very different, for example, than the acceleration due to gravity on the Earth. So that's not a true constant. Okay. The force of gravity will get smaller as the distance away from the Earth increases. Let's just look at an example of someone standing on the surface of the Earth at sea level versus the weight of that same person when they're up in an airplane at a height of more than 12,000 meters above the Earth's surface. An important thing to understand is that r is not the radius. R is the distance between the centers of the two masses. So when someone is on the surface of the Earth, yes, in that situation, r is essentially the radius of the Earth. But when someone is up in the airplane, they're at a high altitude. And so to find the distance between the centers of the masses, you have to add the radius of the Earth plus the altitude to get that r. So the person, even though they have the same mass, their weight will be different at those two locations. At sea level, this 70-gram person would have a weight of 686 newtons. But in the airplane, the person would have a smaller weight of only 684 newtons because the r is larger, right? We're dividing by a bigger number, so we get a smaller force of gravity. I know this doesn't look like a huge difference, but it's important to understand that gravity changes, the force of gravity changes as the distance between the objects changes. In fact, the force of gravity gets smaller as the distance gets bigger. So far we've been talking about the force of gravity. Now let's talk about acceleration due to gravity. That's that lowercase g. And remember, that's not a true constant. It also changes as the distance from the Earth changes. The formula to calculate the acceleration due to gravity is big G, universal gravitational constant, times the big mass. That's the mass of the planet divided by the distance between the center of the planet and the object squared. So it's gm over r squared. So let's go back to the same example of the person initially on the surface of the Earth and then up at the height of an airplane. And we're going to compare the acceleration due to gravity in both of those cases. So on the Earth's surface, if we calculated the acceleration due to gravity, we get 9.799. That's why our commonly accepted value of free fall acceleration is 9.8 meters per second squared. But if we change the r, change the distance between the center of the Earth and the person, it gets bigger when the person is in the airplane. So g would only be 9.762. It's smaller. And I mean, you do need to keep enough significant digits to really see the difference, because that's still a small difference. But the point is that G does decrease as R increases.